Okay, so we're recording. Well, thanks everybody for showing up. The first of our distinguished alumni series to kick off our 100th anniversary season of Colloquia is Professor Greg Bryan of Columbia University. And Greg got his PhD here as an alum in Illinois at let's see, in 1996, working with Mike Norman. And I think you were also kind of half NCSA or something, you had some connection over there. And then went on to a postdoc at MIT before doing Spitzer and Hubble fellowships at Princeton and MIT. Was a lecturer at Oxford for a few years, and then moved to Columbia in 2004. And then since the founding of the Center for Computational Astrophysics at the Flatiron Institute, he's been heavily involved in that, leading a group there. He's the original developer of the adaptive mesh refinement code ENSO, which I believe was one of the first, if not the first, adaptive mesh refinement codes used in astrophysics and cosmology. And so he's worked a lot in galaxy clusters, galaxy evolution, and high performance computational hydrodynamics. And so we're very glad to have him here. And he's going to tell us about. You have your screen, your slides. I'm not seeing them. Go ahead and share them. He's going to be telling us about the Circumgalactic Medium and galaxy evolution.
Yes. Okay, so you should interrupt me if I become inaudible or if I break up or something like that. But thank you, thanks, Paul. I'm really I'm happy to be here. So before I begin, since as Paul said, I am an alumni of. So I graduated in 1996 from University of Illinois, and this is 100 years of astronomy at UIUSC. I thought I would just give a few minutes of my own personal remembrances, and this is 25 years ago. So so apologies to all of those who are much younger than that. But I wanted to say a few things. Pull out a few people. Of course, there were lots of people who influenced me in those years, but two teachers in particular, so Dimitri Michalis and Telemachus Muscovius, really were instrumental in inculcating my love of particularly theoretical astrophysics. I remember Dimitri. I love this picture of Dimitri because he, as far as I know, all my time that I knew him, he never wore a tie. And indeed, so he would give these lectures in which he talked about the sort of beautiful and deep aspects of radiative transfer and computational methods, while showing overheads that were almost unreadable and these old overhead technology. And so one of the things that I got from that was both that it was really important to think deeply about all of the physics going on, but also that it was important to try and use technology to talk to bring things clearly. And Telemachus, of course, I took his introduction to astrophysics class. He I had managed to get through my physics degree without actually learning anything about fluid dynamics or really much about astrophysics at all. It was a physics degree, which meant it was a lot of particle physics. And Telemachus introduced me to both fluid dynamics, but also the importance of trying to describe the problems very simply in key physical ideas. And he would say, probably still says this, it was just freshman physics, by which of course he meant non-ideal magnetohydrodynamics. So I came to Illinois to study star evolution, but I made the mistake of going to this place, this National Center for Supercomputing Applications, which had just started up by Larry Smarr, and hearing a talk given by Mike Norman. And Mike showed beautiful images, movies of fluid dynamics, and I talked to him immediately afterwards, and we hatched this plan to do a thesis on computational cosmology. Little did I know at the time that Mike actually knew absolutely nothing about cosmology. But I'm not sure that would have dissuaded me even if I had known. And then finally, I overlapped, of course, with Yuha, and she didn't do any computation, but she did give me both a real understanding of the complexities of observing and understanding the ISM, and also some skepticism for all of this numerical work. So I hope you'll forgive me for that little interlude, but I remember my time there very fondly, and I wanted to, since this is a special time for you guys, that this is, and for me, I could do this. Anyway, let me get to the meat of the matter, what I want to talk about. So this topic of galactic winds and the circumgalactic medium. So before I get too far, I wanted to say that I want to show you the pictures of the people who actually did the work. So Drummond Fielding is probably the person who's most connected to the work I'm going to talk about. He's a Flatiron Fellow at this Computational First Center for Computational Astrophysics. Matthew Abruzzo and Chris Carr are graduate students at Columbia. Yuan and Miao were also graduate students that now moved on to faculty positions. And Chenggu Kim is a postdoc at Princeton. And then there's a bunch of other people. So the thing I want to talk about then is galaxies, and I think it's a non-controversial statement to say that some galaxies are blessed with lots of fresh fuel for star formation. So this is a galaxy that the Sunflower Galaxy, M63. You can see the beautiful dust lanes in it. Pink here is ongoing star formation. So these galaxies are replete with gas, but of course some galaxies don't. Right? This is NGC 3610, and it has essentially no ongoing star formation. Although it looks very similar. It's a disk galaxy, similar mass. So what sets this? And of course, galaxies come in lots of different varieties and sizes. What controls the gas content, and hence the star formation rate of these galaxies? What is it? Where is it that galaxies get their gas? So here's the Sunflower Galaxy again. And if we look at the immediate surroundings in optical emission, or really almost anything, we see very little except for background systems or a few satellites. And yet these systems are really much larger than they appear. So if so cosmologists like to talk about the virial radius of galaxies, by which we mean the radius within which the mean mass, the mean density within this radius is some fixed fraction, typically a few hundred times the background density of the universe. And this comes from finding the region within which, if this were a top hat, simple collapsing top hat sphere, that the virial radius, the virial theorem, this balance between the kinetic energy of the infall and the potential energy, the gravitational potential energy, would balance, use it with the classical virial ratio. And so this really sets the size of the galaxy. And when we look in optical or really sort of almost any emission, we see very little, as I said, but we know from both inference from gravitational probes, so satellites, things like that there's an enormous amount of matter there. So we've called this dark matter, and we have theories for what this distribution should look like and how it should clump. And here's a result from a simulation. Of course, none of this is directly visible. And I'm not going to talk too much about the dark matter, although it's key for the for controlling the matter, the inflow of gas onto these galaxies. So let me so a picture's worth 1,000 words, a movie's worth many more. Always difficult showing movies over Zoom. They're often jerky, but we'll find out. I deliberately went into a place with a high internet speed, so hopefully this isn't too bad. But this shows a movie made by the code that I developed when I was at Illinois that Paul mentioned. This Enzo code. This is actually not my simulation. This is done by Molly Peebles and Leah Corridos. This is the Foggy team at Space Telescope Science Institute, and they've done a set of simulations in which they look very carefully. They focus an enormous amount of resolution at the gas surrounding the galaxy. So what you saw there was this galaxy forming at the very center. So very dense, very high in heavy elements, metals, and low in temperature. So I don't want to get into too much. I'll show other simulations later. Yes. Sorry, did somebody say something? No. Okay. So one of the things you saw is this complicated inflow of material, and this is what I really want to focus on, is this circumgalactic medium where you see this gas flowing in, you see star formation, supernova, generating outflows, heating the gas. And in particular, you see lots of interaction between cold gas and hot outflows. And that's going to be a theme of what I get through, what I'm going to be talking about. So, so this gas that I showed you before is we have a name now for it. It's the Circumgalactic Medium. There's a review article by Jason Tomlinson and others, and I take this image from that. Shouldn't take it too literally, but this is sort of the picture that galaxy people have of the gas which surrounds galaxies. It's galaxies. Some of it's flowing in, some of it's flowing out. We have this complicated baryon flow, and it's all largely diffuse, meaning that it's something like 10 or 100 times or 1,000 times less dense than even the interstellar medium. So this is truly very diffuse gas. So I said it's there, but how do we know it's there? So when we go, as I keep saying, when we go to actually observe it, we see very little. But we have some clues that it actually does exist. So I'll talk about two and then show a whole bunch of others, the results of a whole bunch of others. So one is the fact that we've now mapped out a few hundred dwarf galaxies around the Milky Way. And so here's the Milky Way. This is hard to see, but I just wanted to stress that there's lots of dwarf galaxies, both around us and around our nearest neighbor, Andromeda Galaxy. And these galaxies, these host of dwarf galaxies, and there's also lots of others in the local group, which are outside of the immediate vicinity of either the Milky Way or the Andromeda Galaxy. And so Mary Putman, faculty here at Columbia, collected together recently the observations of the gas content of those dwarf galaxies. And so this is that plotted as a function of the distance away from us for the sort of brownish points here. And these are all upper limits, meaning that there's very little gas. And this is the same thing for Andromeda. We can't get such good upper limits because we're further away. This is 21 centimeter observations. On the other hand, dwarf galaxies much further away, which are the same stellar mass, we think the same potential well depth, have lots of gas. These are actual detections. So clearly there's something very special, these galaxies which are closer to us, and there seems to be a radius, which is something like 250 or 300 kiloparsecs, excuse me, where beyond which there's a transition, gas rich to within with the virial radius, gas poor. So that's a clue that the gas, this diffuse gas, which they call the circumgalactic medium, is actually affecting these dwarf galaxies near us, is stripping their gas. So that's one clue. A second clue is so one of the galaxies near us is this beautiful pair, the large Magellanic Cloud and the small Magellanic Cloud. So the LMC in particular, we think now, based on its proper motion, is undergoing its first entry into the Milky Way, and is interacting with the gas surrounding the Milky Way. And so we can actually try and model that and compare that to observations. And this was done by, this is some simulations carried out by a graduate student of mine a few years ago, Munir Salem, and he mocked up a model of the LMC and subjected it to a sort of a wind which was too weak or a wind which was too strong. And you could see a strong wind stripped it down to a small radius, whereas weak winds didn't strip it enough. Whereas the Goldilocks wind stripped it to just the same as the observed radius. So this is another clue, again, very circumstantial, but consistent with our estimates of the density of this circumgalactic medium, that it's enough for the ram pressure to strip this gas. So I said there's a whole series of other observations. Here is a nice summary put together by Mark Voigt, who mapped, who combined observations of X-ray emission and absorption measures of gas in the circumgalactic medium, along with absorption line studies, and put together this rough set of constraints showing the inferred density of the circumgalactic medium as a function of radius. And so what you see is that it's very diffuse, as promised. It's many times less dense than the interstellar medium, but nonetheless, there's a consistent set of results which show this nice profile. And we think that the Milky Way is not unusual, that other galaxies also have the circumgalactic medium. So what? Well, as I said, there's strong evidence for the CGM, but what's interesting? Why worry about the circumgalactic medium? Well, as I tried to say before, it surrounds all of these galaxies. This is the way the gas gets in and out of galaxies, and so perhaps this is the gatekeeper. This is the thing which controls whether gas accretes onto galaxies or doesn't, and so controls how much gas galaxies actually have. There's some other evidence that this might be true, because at the cluster scale, so if we talk about not galaxies, but clusters of galaxies, and this is an image of the Perseus cluster. So here on the left is the X-ray image, and on the right is an optical image. You can see all of these. There's some background galaxies, but there's these red galaxies are members of the cluster, and this is approximately the same virial radius, but now these are much bigger objects. So instead of a few hundred kiloparsecs, there are a few thousand kiloparsecs. The gas now here, this circumgalactic medium, and it's really the same thing, is now so hot because we think, just from simple virial arguments, if the gas has that, its thermal energy is in balance with the potential energy, then that temperature goes as the mass, this virial mass, to the 2/3 power, just by simple scaling. And so this temperature now, so for the Milky Way, that virial temperature was of order 1 million degrees, but here is now tens of millions of degrees. And so it's clearly emitting in the X-ray realm, and we can see this gas very clearly emitting. It has lots of interesting structure, but it's not at all clumped like the galaxies. which are more smoothly distributed. There's some interesting thing going on here right at the very center. I'll come back to that in a little bit. So one observation that was made a long time ago is that this gas, since we can see its X-ray emission, is cooling. And it's cooling, and so it's going to, in fact, you can compute its cooling time. So here's a set of clusters. Their cooling time profiles as a function of the radius. So this is a set of about 10 different clusters put together some time ago by Andy Fabian and collaborators. And you can see that these are actually a particular set of clusters which are so-called cool core clusters. They have cool gas in their central regions, and they're cooling fairly rapidly, hundreds of millions of years in the center. Certainly much younger than the age of the universe or the age of the cluster. So that gas must be going somewhere. But one of the puzzles, of course, of these clusters is that they show very little star formation. So this was a puzzle for a long time. Its resolution is now fairly clear that there's some sort of feedback from the jet or from the black hole, accretion onto the black hole at the center of these objects. They're driving jets which heat up this gas. And as I mentioned, if we look very closely at the center of the Perseus cluster, we can actually see this cold gas. So these are H-alpha filaments surrounding this thing. And remember, this is swimming in a sea of X-ray gas. So once again, here, we're seeing this very close interaction between cold gas, this H-alpha emitting gas. So that's, by cold here, I mean 10 to the 4 degrees. So still hot, of course, but much colder than the surrounding gas here, which is invisible, which is tens of millions. So, and some of this gas is even forming young stars, not anywhere at the rate we would predict if just by taking the amount of gas here and dividing by the cooling time. So something is preventing most of the gas from cooling and forming stars. And of course, there's now lots of evidence that this is this AGN feedback, this jet-driven accretion. Here, for example, is radio emission from the center of a different cluster, and this is the relativistic particles from the jet, and this blue here is the X-ray emitting gas. And you can see there's cavities here, and so there's clearly an interaction here. There's some sort of heating. So it's long been postulated that there is a feedback cycle. Gas accretes onto the black hole, drives some sort of jet, which heats up the galaxy. And so Yuan Li and I worked on simulations, again, using the same code, Illinois developed code. This is focusing in just on the center of a cluster like Perseus. And what I hope you could see there was that there was lots of gas condensing and precipitating out of this hot region around. So this is, as I said, focusing on pretty much the very center, 40 or in this case about 80 kiloparsecs around the center of the cluster. The simulation extends much further, but we're just focusing on this. And we put a black hole at the center here and put a simple model for driving jet. And what we found, what Yuan found was that this system just generically self-regulates. That heating over a long period of time will balance cooling. And so indeed sets up exactly as we suggested, this picture of self-regulation. This AGN feedback balances cooling. And Yuan was very interested in comparing against observations. And so here is a simulated map on the right, showing the X-ray emission, these hot bubbles, showing the jet, the shocks driven by the AGN jets, which are not shown here, and lots of cold gas clouds. Here shown is H-alpha emission. So this is a combined X-ray and H-alpha emission map. to be compared with the same thing on the left. This actually includes the radio emission from the jet as well. But so you can see the morphology is similar. It's maybe hard to see, but there are shocks along here in the X-ray emission, and there's lots of filamentary emission in the HL. So this is evidence that this model, this simulation of this feedback can reproduce many of the observations in detail of these systems. So once again, I'll stress this interaction between the cold and the hot gas. I'll come back to that. So, but one of the questions is, of course, how does the black hole know when to send its jet? I mean, obviously when gas accretes, but in detail, what is this regulation mechanism? This is a question that has because is challenging, because the black hole is of course operating on very small scales, where accretion is occurring at the Schwarzschild radius or a few times it, or in the accretion disk, whereas most of the cooling is coming at hundreds of kiloparsecs out. So there has to be this regulation mechanism, and in detail, we weren't the first, but we agreed that this idea of precipitation, in fact, the seminal paper came out a few years before that by Mike McCourt, not quite without the jet, but we were showing here for the first time that the jet agreed with this picture, that whenever the cooling time of the plasma, in the cluster dropped below a certain level, and McCourt et al. Postulated that there was this crucial ratio of the cooling time to the freefall time, which was a factor of order 10, and that whenever it dropped below that, these cold gas clouds would precipitate out, fall towards the center, accrete onto the black hole, and drive an outflow, which then heated things up. And you can see that operating here. The cold, this is the cooling time dropping below 10, and then a little bit, and this is the black hole accretion rate. You can see that a little bit later, a few 100 million years later, after those clouds have fallen in, drives accretion and hence jet feedback. So you notice there's a time delay between the cooling and the feedback, and this is important because this causes an overshoot, and so that's what causes the cyclical nature of the jet. That in detail, at any particular instant, it's not in balance, but over hundreds of millions of years, it is. So, Mark Voigt, of course, is one of the people who have explored this model in a lot of detail. He's written a whole series of papers, some of which I've helped with on the simulation side. Here's a beautiful set of observations which put together, which shows evidence for this precipitation. So this, I won't get into a lot of detail, but basically this is a set from a bunch of different X-ray clusters looking at the cooling time against the radius for the clusters which show multiphase gas in the center, so like those H-alpha filaments, versus those that don't. And you can see that the ones that don't have long cooling times, the ones that do have short cooling times, but they don't fall below this precipitation limit, where the cooling time to the free fall time is of order 10. So there's now a whole body of work, and I think the evidence for this precipitation-driven feedback in X-ray clusters is quite strong. But I've always really been interested in galaxies, even though I ended up doing my thesis on X-ray clusters, and I wanted to know, would this same mechanism work for the circumgalactic medium around regular sized galaxies? In other words, could we replace this black hole feedback, because lower mass galaxies don't have black holes in their centers, or they have, more precisely, they have much lower mass black holes, which are not producing energetic jets, which can self-regulate. Could we replace it with supernova feedback, but keep the same precipitation frame? And Mark and I explored this idea a few years ago, and we developed a simple model which was able to predict the fraction of the gas inside each halo, which would be turned into stars according to this precipitation model. So we just forced the cooling time, the free fall time to be 10, and asked how much gas would then turn into stars. And what we found is that it's a falling fraction as you go to lower masses. So this is the circular velocity. These are dwarf galaxies over here. These are high mass galaxies over here. And what we found is that the model naturally predicts this fall off to decreasing mass. Now, that's traditionally explained, again, still by feedback from star formation, but it has to be put in by hand, that supernovae somehow drive more efficient outflows. You know, the gas all falls into the galaxy, the supernova drives it back out, and that this decrease from a baryon fraction of 1, which would occur if all of the gas fill into the galaxies, is put in by hand. Whereas this falls out basically from the atomic physics, because this cooling time is constrained by the cooling of the gas. So this is, yeah.
So yeah, before you go on, I have a sort of a remedial question. So about the precipitation picture. So how am I supposed to have this in my head? So is the idea that they're little cold clouds that are sort of like droplets that fall in?
Yeah, that's right. So the theories like this actually turn out to be quite, so in fact, this is work that Chris Korn or Gregson here are doing. We've sort of tried to generalize this to a set of models, not just precipitation, but any models in which the circumgalactic medium is controlled by cooling. That for a wide class of models in which this cooling occurs, we don't know exactly why. Maybe it's filaments, maybe it's clumps. We try to generalize this. But yes, in terms of this precipitation picture, the idea is that it's really gas clumps which condense out, hence the name, and because they're anti-buoyant, fall towards the center. So in the case of galaxies, they would fall onto the galactic disk, become part of the ISM, eventually form massive stars, explode as supernova, drive outflows, which heat up the circumgalactic medium.
Got it. Thanks. And so how big are these things? Do you resolve them out, the clumps?
In the simulations, absolutely not. They're not resolved. And in fact, that's what I'm going to come back to. So I'm glad you asked that question. Keep it in mind. Yes. So in fact, here's the question. So what is actually driving this on the galactic scale? What would this look like? What would this picture look like? And so there's a couple of, so what I've stressed so far is the precipitation picture in which cold clumps condense out and fall into the galaxy. But actually, galactic winds are sort of the inverse problem. So this is M82. For those of you who know galaxies, I think you probably know what's coming. But this is a galaxy which we know is bursting with stars. Young, big stars are exploding in the center at a rate which is something like 10 or 20 times the rate of our own galaxy. So this is a starburst. And one thing that's observed in this galaxy is cold clouds. So this material here, this is all H alpha emission, and I use cold throughout, and I'll stress that over and over again, cold to mean 10 to the 4 degrees. So everybody's definition, cold and hot, is different. This is going to be mine. Cold is 10 to the 4, hot is 1 million or larger. So these cold clouds are actually moving outwards, away from the galaxy. We know that from their Doppler shifts, other evidence, and that's probably being driven by the star formation at the center. So there's no significant AGN going on here. So this is not like the kind of feedback I was showing you before. But it's not just cold clouds. We know that because there's X-ray emission. So this is the same thing, but now with X-ray emission overlaid. In blue here, and you can see that there's again this interaction between cold clouds and this hot medium. So what's going on here? So this is very similar to precipitation, but in sort of backwards, right? I mean, this is driving stuff out. So how can these cold clouds and this hot medium be interacting? What is their interaction? We need to know that both for understanding if precipitation is correct, because as you pointed out, the simulations can't really resolve those cold clouds, but we also need to understand that if we're going to understand how this outflow, what's important here is, are the cold clouds being launched somehow by some sort of ram pressure? That's the traditional explanation. And just because I love simulations, show you a little simulation of this, just to show that the simulations, it's going to be jerky on. So let me not stress that, but let me just stress that these simulations, as Paul just said, are really hard to simulate because we're trying to simulate the entire galaxy, but also individual clouds within the galaxy. So here's sort of a schematic. And in order to try and understand this interaction between the hot gas and the cold cloud, we're going to focus in on the boundary layer. So I'm going to show you that in a little bit in order to get enough resolution to try and understand what's really going on here to resolve this. So just to stress what I've just said, what happens when this hot, high velocity gas interacts with the cold clouds in the interstellar medium? In fact, that's really the key question that I think is if we want to understand the circumgalactic medium or X-ray clusters or galactic winds or ram pressure stripping, all of these things, we need to be able to answer this question. And so over the last few years, that's what I've been focusing on. Let me say there's a very nice paper by Dongjing, which sets the key question in this area, which is, so this paper was called Entrainment in Trouble because it raised this following puzzle. So this is a hot wind. This is a very simple schematic picture of what I've been describing. Here's a cold, we're theorists, so we want to talk about things which are spherical clouds. And here's this hot wind, which is hitting this. The time taken to accelerate this cloud significantly is really just the amount of time that it takes to sweep up the similar amount of momentum. So we can define an acceleration time, which is just the cloud radius divided by the velocity of the wind times this factor chi, which is the density contrast between the cold cloud and the hot wind. So here's a simulation. So this is done by Matthew Abruzzo, graduate student here at Columbia. And indeed, as many people have shown in the past, these clouds, when you project them, are destroyed. The destruction time to the acceleration time is actually this ratio of chi to the -1/2 power, and because chi, the density contrast is very large, it's hundreds of thousands, then this number is very small. These clouds are destroyed. Cloud crushing time is shorter than the acceleration time. So that's a problem, and that's the problem. That's why it's paradoxical that we see these cold clouds in the M82 wind at all. They should not be there because of this simple argument. Something has to be going on. There's lots of theories. Maybe radiation drives it. Maybe there are fields. I think there's problems with all of those explanations. But Max Gronke and Peng O suggested something a few years ago. They pointed out something that actually a number of people should have caught, including myself. But there is a parameter space in which the rate of cooling can save the day. So if, as they pointed out, the cooling time in that of gas in the layer, and I'll get into this in a bit more detail, between the hot and the cold clouds is short, and shorter in particular, less than this destruction time, then the cloud can survive for a long period of time. So one can characterize this as a minimum cloud radius. The cloud has to be big enough that this mixing is not efficient enough, and cooling can save it. And so they showed with simulations, here's again a nice simulation by Matthew, just to try and convince you that this is actually true. It's exactly the same code, just in this case, a different parameter space, where we subject this cold cloud to a wind, but now that interface layer can cool. And you can see it, it's spectacular, right? It forms this long tail. Let me just show that. This long convoluted tail with this complicated boundary. And these are of course are high resolution simulations, and this is a converged result. By which I mean that as we increase the resolution, the mass of the cloud as a function of time is independent of the resolution that we put in. Although the individual folds and features here are not robust, they change. But that general result that the cloud survives is robust. We've gone to very high resolution. So what's going on? How do we understand this? So here's a very schematic picture of a cloud, and I'm afraid I've reversed the direction of the wind here. The wind is now coming from the right, then this cloud is being stripped here. And as I said before, what we want to really do is try and understand this turbulent radiative mixing, this interface between the cold and the hot. And to set the problem, we're going to do simulations just of that interface layer. So just of this box here, hot gas on the top, cold gas on the bottom, and there's a shear flow. It's going to drive some turbulent mixing. The hot gas is radiatively inefficient. The cold gas is radiatively inefficient, but there's gas at this interface temperature, which is very radiatively efficient. So almost all of the radiation is coming from gas at this interface layer. That's important. The cold and the hot gas is stable by itself. If the interface layer went there, this would be a stable situation. So that cooling turns out to drive condensation. It drives a slow but steady inflow of hot gas onto this interface layer. And that's actually what drives the growth of the cloud, because actually the clouds don't just survive in the right parameter regime, they actually grow. Hot gas condenses onto this. So here's a simulation to try and just to show you that this is the evolution of this is complicated. So these are different panels. Let me just stop it. Oops, sorry. These are different panels here showing on the left, the density, the temperature, the vertical velocity. So bright here, up at the top here is going to be inflow. And this is, we're trying to pull out the turbulent velocity of this interface. So let me just play that movie again. So initially the interface is very flat. We initialize it with a very small perturbation. That perturbation grows and this turbulence sustains itself. And this interface layer is cooling, and you can see it's incredibly complicated. This is a slice from a 3D simulation. So it's not like these clouds are just appearing out of nowhere. There's some complicated structure, and I'll show you a visualization. In fact, what I sent, the image that I sent around was a visualization of that interface surface. In fact, let me show you that. Oh, actually, before I do, let me talk a little bit about the theories which might actually be driving that flow of hot gas onto the interface layer. So here, so when Drummond and I looked at this, here was the prevailing theory for what drives that interface, drives that flow. So here's the hot end, here's the cold end. And what people saw was that there was a pressure dip that was introduced. The rate of cooling occurred at this interface level layer, decreased the pressure, and the argument was that this pressure gradient drove an inflow from the hot gas. So that drove the inflow driven by this pressure gradient, which seemed completely reasonable. and is what I'll call the sort of waterfall picture. So so we tested this, and here's a simulation. This is a low resolution simulation. So here's the pressure, and for various reasons, we parameterize this not as the distance along that interface, but as the entropy along that interface. But it doesn't matter, you can think of this as the distance. This is the hot end, this is the cold end, and here's that pressure dip that we were talking about. So the only problem is that, so we did a simulation with low resolution, found this pressure dip. We did a simulation with medium resolution, found a smaller pressure dip that was worrying, and then did a higher resolution simulation and found no pressure dip at all. So maybe that's okay. Maybe there's a big inflow here and there's no inflow here. Turns out that's not right. All of those simulations, except for the lowest resolution one, are consistent with the same inflow velocity of the hot gas. In other words, that condensation is as I mentioned before, is well resolved. It actually doesn't take surprisingly little numerical resolution to resolve that interface. And the inflow doesn't depend on the pressure dip. So that pressure dip, while a feeling theory, turns out to be wrong. And so we postulated a different idea, that it's really the mixing at that interface which drives this. So of course, this interface layer is unstable to Kelvin-Helmholtz instabilities. And so we're going to postulate this water wheel theory rather than the waterfall theory. And the idea goes like this, that really it's this mixing is driven by turbulence. And of course, turbulence is this cascade. Kolmogorov told us that there's this cascade from small to large, and the energy dissipates at small scale, and that's where the cooling occurs. And so in detail, of course, there's the driving scale, that's the size of the cloud in this picture, and then there's a dissipation scale. And the turbulent velocity goes as the scaling, this Kolmogorov turbulence scaling. But one of the interesting things is when we looked at that interface layer, at smaller and smaller scales, it became increasingly complicated. In fact, when we looked at it carefully, and this took embarrassing a lot of time to realize, we realized that interface layer is fractal. So here's that visualization I sent around. And what we found when we looked carefully is that as we smoothed it, the area systematically changed. In fact, it looked a lot like a Koch curve, as such that the area scaled with this averaging length to the -1/2 power, or in other words, it had a fractal dimension of 2.5. So that was the key insight then, which let us determine. So I won't go into the details of what the theory looks like, but the idea is that the cooling occurs at this highly convoluted interface level layer, and so the area depends on the cooling rate depends on the area, which depends on this length scale you smooth it to. Now that might sound like it should depend on resolution, but it turns out that the cooling picks out a particular length scale in this turbulent cascade. And as long as you resolve that, and that's actually not that small, that you don't have to resolve the rest of the cascade in order to get the turbulent cooling rate right. So this then allowed us to formulate a simple theory. And again, I'm not going to go into the details, but so Drummond did a whole series of simulations. This is the result of hundreds of different simulations, like I showed you before. And this scaling is the simple, this power law scaling. It's not because of the combination of cooling and turbulence and this fractal nature. The exponents here are not obvious. You can look at the paper for derivation, but really this comes from simple balance of inflow of energy from the hot layer balancing cooling at that fractal layer. And so the simulations nicely match this simple theory. So great. What about real galactic winds? The outflow. So what about real galactic winds? How does this new idea about what governs the mixing between the hot and the cold phases play out? Well, so I won't go into that in much detail. In fact, this is all I'm really going to show on this, because this is, I'll refer you to this paper, which just came out on AstroPH a few weeks ago, in which we lay out a theory which uses this insight, we call it turmoil, sort of turbulent radiative mixing layer, between the cold cloud and the hot interface. And we write down the equations which govern the interaction between these cold clouds and the hot outflow, this hot supernova-driven outflow. So as it still has that same basic property, when the cooling time at the interface layer is short compared to the mixing time, the cloud grows. When the mixing time is short compared to the cooling time, the cloud is destroyed or shredded or mixed into the hot gas. But it's more complicated than that, because the cold clouds aren't just impacted. So that's the impact of the hot wind on the cold clouds, but it goes vice versa. And that's the real interesting thing that we laid out in this paper. It has a set of effects on the hot wind. It decelerates the wind because of the momentum transfer, but it also heats up the gas, the hot wind. And this actually addresses a long-standing conundrum with those hot winds that I was talking about, which is that as in fact, there's a paper by Chevalier and Clegg in 1985, which shows this beautifully, writes down the analytic results, and shows that as this wind expands, that it should adiabatically cool and very rapidly stop emitting X-rays. And yet we see X-rays from galaxies like M82 for a large distance. So, and this, I think, explains that by the fact that the hot medium actually shocks against these cold clouds and heats back up. They can also gain mass. So this mass, momentum, and energy exchange between the hot and the cold are the set of equations that we wrote down here. And I'll refer you to that for detailed results. What we found basically is that it is important, and it's not a complete explanation of all of this, but it's an important step along the way. We hope to be able to put this. So we developed a simple analytic theory. As I stressed before, one of the problems of doing these simulations is that we can't resolve this interface. But with this theory, hopefully now we can write down a subgrid model for this interaction between the hot and the cold gas, and be able to actually do these simulations in which we get this interaction between the cold and the hot right. So that's future work. So let me just put up my summary. Circumgalactic medium exists, we think. I look forward to, there's promising observational missions being planned, which actually may be able to image it directly. This precipitation picture, there's lots of evidence that it's operating on cluster scales. And it's very interesting to think that it might be operating on the circumgalactic scale for Milky Way sized galaxies and below. And then finally, this turbulent radiative mixing layer results are very interesting. We think this idea that this boundary is a fractal is important to understanding how that interface actually operates. And I have to say that a lot of this analysis and image generation was done with YT, an Illinois project. So thank you, Matt. Now let me stop.
Thanks very much, Greg. So we have time for questions. Anybody? Yes, Charles.
Yeah, hi, Greg. I'll ask Telemachus's question before he gets a chance to. So what about magnetic fields and what about conduction?
Yes, good. I think those are both very important. So I didn't say this, but actually we've done all these cloud crushing simulations with magnetic fields as well. It introduces a whole set of other scalings, both dependence on the strength of the field, but also dependence on the topology of the field. And so let me actually address the dynamical effects of magnetic fields first. And I didn't go into this. There's some, if the field is strong enough, if it's dynamically important within the cold clouds, and that's important, not just in the hot medium, but actually if you put in cold clouds with a strong magnetic field, and by strong I mean beta values of order unity, then that actually can help hold the cloud together, and then actually largely because it suppresses instabilities at the surface, and so damps the mixing, and so keeps the cloud coherent, and then the cloud can actually accelerate. So this is another method that we've been exploring. I think it's very interesting. It's unclear. So it requires a strong magnetic field in the clouds. It's unclear if real clouds have these strong magnetic fields, of course. For a variety of reasons, my suspicion is that they don't, but I think that's at this stage just a suspicion. So I think that's an important area to look at more. It does have some interesting effects on these turbulent radiative mixing layers because it suppresses the mixing, and so it suppresses the cooling. So this is another thing that we can test. So that's one important question. And the other, which is non-ideal effects, so in particular conduction, is really important. And so we've also looked at that. So of course, these things are not independent. The fields actually can suppress conduction. There's other things which can suppress conduction. So the strength of the conduction across the interface is uncertain. For a variety of reasons, I suspect it's not as strong as Spitzer, but its strength is unknown. The effect, interesting. So we looked at this particularly in the galactic outflow case, and the effect is interesting. It turns out that if you include conduction at a reasonable fraction of Spitzer or below, then the clouds which are destroyed by conduction are those which would have been destroyed by turbulent mixing anyway. It's a coincidence that the numbers are very similar because, of course, one has to do with the turbulent velocities, and the other has to do with conduction, which are dependent, of course, on atomic properties. But it seems coincidentally to work out that either thermal conduction can destroy the small clouds, or turbulent mixing. However, the large clouds, those which are going to grow, I don't seem to be affected by conduction. Now, this is, of course, depends on the hot, the medium of the temperature of the hot medium. If we ramp up to the cluster scale, then conduction is going to be quite important for the destruction of those clouds. So everything I've said so far really has to do with the Milky Way scale.
Thank you.
May
I? Sure, since this is, directly your wheelhouse. Yeah, go ahead, Telemachus.
Well, Charles asked half of my question and Greg responded to 3/4 of that. So I'll ask the remaining 1/4 and then an observational question. The picture you presented, Greg, seems to imply that the magnetic field will be quite messy, high above the galactic plane or below it. Now, we know that there are excellent Faraday rotation observations from other galaxies that show quite a large rotation measure, which would seem to be contradicting the picture of a very messy magnetic field surrounding our galaxy. Could you comment on that? And then I'll have an observational question.
Absolutely, I think that's an excellent question. So I would differentiate between the field strength in the hot phase and the fields in the cold, in these turbulent radiative mixing layers. So one thing which I want to stress is that the volume filling factor of these radiative mixing layers is very small. And so if your magnetic field probes are primarily volume, probing the volume of the circumgalactic medium, then most of that is filled with this hot gas, which is flowing out. And the turbulence there is the turbulent Mach number is relatively small. It's only at the interface layers that the turbulent Mach numbers become large. And then within the clouds, exactly as you say, I would expect that the fields would be messy. So as far as I know, that's yeah.
Thank you.
Your
The
observational
observational question. If you look straight up or straight down towards the galactic poles, what kind of column density of what you call cool gas would you expect? And would that be consistent with the very old observations of H1 emission by Nanielu, Dieter, and others, that they see a column density of about 10 to the 19 particles per square centimeter?
You mean looking down on the, I'm not quite sure I understand the topology. Looking down on the poles?
Now, from where we are,
Yeah.
take your radio telescope and observe H1 straight up towards the galactic North Pole or straight down. You will see some emission of H1. What column density would your simulations predict, and how does that compare with the very old observations?
Excellent. Yes. So we don't yet have a prediction either for the so that's, you know, this is this is actually something we're actively working on for predictions for the H1 emission, the H alpha emission, and also metal line probes, carbon 4, oxygen 6, which we think can probe that interface layer. So I think that's an excellent question, and you know, observational comparisons is something that we're keen to do.
Bryan?
Thank you.
Yeah, thanks for your talk. So Telemachus's question started to get at what I was interested in too, and so did you. So the metals. So what's the metallicity of the wind coming out? So I guess it's some combination of supernova ejecta and interstellar medium.
Yeah. So this is very interesting. The wind itself. So the very hot. So it's, yeah, that's a really good question. And so this is an area that we've been looking at. So it's exactly as you say. It's some mixture of the eject itself, which of course would be supersolar, right? Would be very high metallicity, mixed with the clouds as they're coming out. So I didn't talk about this, but another set of projects that we're doing is simulations which just try and focus on a small portion of the disk. Because if we want in detail to predict how much mixing is going on and the outflow, then we need to know how much mixing is going on within the ISM itself, which is driving this. So this is Chang-Gu Kim, Miao Li, have been doing these sorts of simulations, and the metallicity of the hot outflow has actually high, of the wind itself seems to have a high metallicity from these simulations. So that's the early indication that it's high in specific energy and it's high in metals, because the amount of mixing with the rest of the ISM is relatively small, but not zero. So if you want specific predictions for that, Chang-Gu Kim has a paper, well, he's the lead author, which lays out very specific metal loading factors as a function from these sorts of simulations as a function of stellar star formation rate, surface density.
Cool, thanks.
Okay, I don't see any more hands. We've passed an hour. So let's thank Greg, and thanks again, Greg, for coming.
Paul, you're really soft.
Oh. Sorry, my microphone is constantly resetting itself. Yeah, thanks. Thanks again, Greg. And I don't see any more questions, so we've passed the hour. And so let's thank Greg again. And if you have more questions, I'm sure you'll be happy to address them via email.
Thank you, and thanks to all of you. And congratulations on your 100 years of astronomy at Illinois.
Excellent work, Greg. Congratulations. It's good to see you, however, virtually. Maybe
Yes.
someday you'll come here.
I would love to. I miss it.
We'd love to see you. Take care.
You too.
Bye-bye, Greg.
Bye.